Welcome to Daily Papers, the podcast where we break down fascinating new research. Today, we're asking a huge question. Can AI actually do science?
We're not talking about an AI that can help a scientist with data analysis. We're asking if a large language model, like the ones we hear about every day, could be a scientist itself. Could it discover a new law of physics?
It's a tricky question, because how do you test that? You could give an AI a bunch of high school physics problems, and today's models are actually really good at those. But does that mean they understand physics?
Exactly. Or did they just memorize the solutions from all the textbooks and websites they were trained on? It's the classic reasoning versus recitation problem. Are they thinking, or are they just pattern matching on a massive scale?
A new paper titled Testing Frontier Large Language Models Physics Literacy in Parallel Physical Worlds has a brilliant way to solve this. If you want to know if an AI can really reason about physics, don't test it on our physics.
Test it on physics from a parallel universe. The researchers created 3 different worlds, each with its own unique and unfamiliar set of physical laws. The AI can't have seen the answers to these problems before because the worlds are completely made up. It has to reason from scratch.
This is such a cool idea. Let's talk about these worlds. The first one, the easy world, makes just one little tweak to a rule everyone learns in school, Newton's second law, F equals ma.
Right, force equals mass times acceleration. In our world, if you apply a constant push to something, it constantly speeds up. But in this first fake world, the law is F equals mv, force equals mass times velocity. That means a constant push gives you a constant speed. The moment you stop pushing, the object stops dead, no coasting.
A subtle but fundamental difference. The next world, the medium one, is actually not fake. It's historical. It's Aristotelian mechanics.
This is the physics of ancient Greece. Heavy objects fall faster than light ones. Things move towards their natural place. Smoke goes up, rocks fall down, and so on. The challenge here is that the AI has been trained on a mountain of data that essentially screams Aristotle was wrong. So the question is, can the AI suspend its training and reason logically inside a framework it's been taught to dismiss?
And finally, we get to the hard world, which the authors call decay world. This one is truly weird. The one and only rule is that every physical quantity, speed, temperature, rotation, even the radius of an orbit, loses exactly 1% of its value every second.
And there's no reason for it. It's not because of friction or air resistance or heat loss. Those are all explicitly turned off. It's just a fundamental universal law of decay. It's a huge cognitive challenge because you have to apply this one weird rule to completely different situations, mechanical, thermal, orbital, all at once.
So these are the exams, but it's not just a pass-fail test. The researchers break down the scientific method into a 4-stage obstacle course for the AI.
First is induction. The AI is given a list of observations from one of these worlds, like a cart stops the instant the push ends, and it has to figure out the underlying rule.
Second is formulation. The AI has to write down the rules it just discovered in a clear, precise way that someone else could use.
Third is prediction. It takes its own rules from stage 2 and uses them to predict what will happen in a new scenario. For example, if a heavy block and a light block are pushed with the same force, which one will go faster?
And finally, stage 4 is review. The AI has to look back at everything it just did and check for its own mistakes, a self-correction step.
Okay, so we have 3 bizarre worlds and a 4-stage scientific boot camp. How did the AIs do?
The short answer, not very well. In the easy and medium worlds, the top models passed only 6 out of 15 times. That's a 40% success rate.
And in the hard decay world?
0. A big, fat 0 out of 15. Not a single model managed to pass all the stages.
Wow. But as the paper points out, the final score isn't the most interesting part. It's where and how they failed that's really revealing.
Absolutely. In the medium Aristotelian world, the biggest hurdle for the models was stage 1, induction. They just couldn't stop themselves from bringing in concepts from modern physics. They'd try to correct Aristotle, talking about friction or gravity, even though those words were banned. They couldn't suppress their training.
But the most fascinating failure happened in the hard decay world. Remember, everything loses 1% of its value every second. When it came to the prediction stage, something amazing happened. The models were almost perfect at predicting the direction of change.
Right, they knew the hot water would get cooler, the spinning top would slow down, the orbit would shrink. They got the qualitative picture perfectly, but when they were asked to calculate how much cooler or slower it would be, they got it wrong a huge chunk of the time.
How did they get it wrong?
They fell back on standard physics from our world. Even though concepts like energy were explicitly banned, the models would secretly use equations for energy loss to do the math, which gave the wrong numbers in this world. It's like their qualitative intuition is good, but their quantitative calculation is rigidly stuck to the physics they were trained on.
That is so interesting. Their gut feeling is right, but they can't do the math without reverting to what they know. What about that last stage, the self-review? Could they catch their own mistakes?
Not at all. This might be one of the most important findings. When a model failed a trial by making a mistake in the first 3 stages, it went on to stage 4 and had to review its work. In 2/3 of those cases, or even more, the model reported that it had made no errors.
So they're confidently incorrect. They mess up, and then when you ask them to double-check their homework, they look it over and say, "Looks perfect to me."
Exactly. So what does this all tell us? Large language models aren't about to start discovering new physics on their own. They struggle immensely when they're pushed outside their training data into a world with truly unfamiliar rules.
But it also shows us where their strengths and weaknesses are. They have a surprisingly good qualitative intuition, but it's brittle and it breaks when it has to get specific and quantitative. And they are not very good at spotting their own flaws.
This paper doesn't just give us a grade for today's AI, it gives us a much better way to test them. By creating these parallel worlds, we can finally start to untangle what they're truly thinking from what they're just remembering.
It's a huge step forward in figuring out what's really going on inside these complex systems. That's all the time we have for today. Thanks for tuning in to Daily Papers.